In section 5.6, we're going to look at integration using a particular method called substitution. When we use substitution, we basically get to integrate a whole large set of integrals that we couldn't work with before. We can integrate composite functions, which is basically looking at the chain rule in reverse. And we need to keep in mind that integration is a lot more complicated than differentiation. So sometimes we'll come across things that we can't integrate using our antiderivatives, using our trig functions, and also using this technique of substitution. We'll learn a lot more methods when we get into Calc 2. The best way to start is to just go ahead and start looking at some examples. Our first example, we're going to be looking at the integral of 2x times x squared plus 1 to the 4th dx. Now if you look at this particular integral, it's a composite function. This is one function, x squared plus 1, and then I have something raised to the 4th power. That's the composite component. And then I also have a product here. I don't want you to think that this is the product rule. What we're going to do here is called U-Substitution. Now what we like to do is we like to choose a value for u, and sometimes you can use w or v instead of the letter u, but u is the most common. And we're going to choose a value of u and then find a du. And then hopefully in between what I have for u and du, everything will be represented that's in the integrand. Usually you choose the most complicated part to be your u. You usually choose the highest degree. Now you might say, well, 4 is the highest degree here, but remember that's to a power, so I choose the base of x squared plus 1. If u is x squared plus 1, du is 2x dx. Now the dx comes from the fact that this is over du dx, and then you multiply both sides through by dx. Now if we look at this, I have everything represented. The 2x dx is my du, so 2x dx makes up my du, and then this x squared plus 1 to the 4th is u to the 4th. So when we rewrite this, u to the 4th, because u is x squared plus 1 to the 4th, and then 2x dx is my du. So this is rewritten as the integral of u to the 4th du, which is really easy to integrate. This is our good old power rule, add 1, divide by the sum. So this integrates into u to the 5th over 5. But I'm not done yet. My original integrand was in terms of x, and so should my solution be. Right now my solution is terms in u, so I need to substitute back in. Now remember, u was x squared plus 1, so this is going to be x squared plus 1 quantity to the 5th over 5 plus c. And that's my solution using U-Substitution. Now remember, we can check every single one of these by taking the derivative of our solution, and hopefully we'll get our integrand back. Now to take our derivative, we have to remember, we're taking derivatives, so we bring the 5 down, decrease the exponent by 1, and then we multiply it by the derivative within. And then don't forget we have this 5 in our denominator as well. The derivative of a constant is 0, and simplifying we have 2x times x squared plus 1 to the 4th, which is exactly what we have up here, so it does check. So remember, we can check all of these problems by taking the derivative. Now when we're looking at a definite integral, you'd want to check before you evaluate. Let's look at the integral of 3x squared times the square root of x cubed plus 1 dx. Okay, again, U-Substitution says choose the highest power here, because when I take a derivative, the power decreases by 1. Now that's not a surefire substitution all the time, but it is a good place to start. So u is x cubed plus 1. Du then would be the derivative of x cubed plus 1, which is 3x squared dx. Now remember, this dx comes from the fact that I'm taking du dx, the derivative of u with respect to x, and then I multiply through both sides by dx. Substituting back in then, 3x squared dx makes up my du, and then this component right here, this radical, is u to the 1/2 power. So rewriting, I have u to the 1/2 du. And using our good old power rule, add 1, divide by the sum, I get u to the 3/2 divided by 3/2. Now remember, my original integrand was in terms of x, and so should my solution be. So let's go ahead and rewrite. This would be 2/3 u to the 3/2, but u was x cubed plus 1 to the 3/2. This is an indefinite integral, so I have my constant of integration, and that's my solution. Now remember, I could check this by taking the derivative. Now the one thing we want to remember here is the integral of this product. I have a product whose factors are 3x squared in this radical. The integral of a product is not the product of the integrals, meaning I just can't integrate 3x squared and then integrate this component separately. I need to make sure that I have the u to u occurring there. Let's go ahead and look at one more before we look at a little bit more complicated type of integrand. Let's look at the integral of secant squared of x times the quantity tangent of x plus 3. Now this one's not so obvious. You might think, well, u should be secant because that's my highest power, but trig functions don't always work like that. Sometimes they do, sometimes they don't. And of course I have a dx here. Now for this one, I need to think about derivatives and antiderivatives. The derivative of tangent is secant squared. So this should work pretty slick. And actually we need to clean this up a little bit. That plus 3, get that in there, tangent of x plus 3. The argument here is just x. The way I had it written, the argument was x plus 3. And then this method wouldn't work. I'd have to rewrite this using some trig identities. So in this particular case, we're going to let u equal not just tangent of x, but tangent of x plus 3. Now again, this is a trial and error process a lot of times. Sometimes you'll choose a u that doesn't work. Now the derivative of tangent is secant squared of x. The derivative of 3 is 0, and of course I have my dx here. Now when we rewrite this, this is my u. Secant squared x dx is my du. So rewriting, I'd have the integral of u du, which is just u squared over 2. My solution right now is in terms of u, and it needs to be in terms of x, so I need to substitute back in. U was this entire binomial tangent of x, and remember, x is the argument of my trig function, plus 3 quantity squared all over 2 plus c. That's my solution. Now remember, we could check this by taking the derivative. Okay, now we get into the little bit more complicated pieces. This is called compensation. Now in this particular method, these problems look very similar to the ones we just did, except for I don't have a du exactly. So in this case, again, I'll choose my u to be the base. The highest power here is x squared minus 2. Du then is 2x dx. Now we have the x right here, but we need a 2 times x. And what we can do is we can basically multiply by 1 to get that. 2 over 2 is the same as 1. I want the 2x together, so I multiply by a 2 on the inside. But if I multiply it by a 2 on the inside, I have to compensate with a 1/2 on the outside. This is called compensation. So when I rewrite this, then I have 1/2 integral. Now remember, 2x dx makes up my du. 2x dx is my du. X squared minus 2 is u, so I have u to the 1/2 du. Now where did this 1/2 come from? The 1/2 came from the fact that I was missing a 2. If I multiply by a 2 on the inside, I multiply by a 1/2 on the outside, the overall effect is I've multiplied by 1, which is the multiplicative identity, which means I have not changed the value of the integrand. This is called compensation, and we're going to be using it a lot. Then we integrate as usual. U to the 1/2, I'd add 1. U to the 3/2 divided by 3/2. When you divide by a fraction, you multiply by the reciprocal, so dividing by 3/2 becomes multiplying by 2/3. U to the 3/2. U in this case was x squared minus 2 to the 3/2. 2's cancel. 1/3 integral x squared minus 2 to the 3/2 plus c. That's my solution. Now remember, indefinite integral, you need to have that plus c. Another thing to keep in mind is sometimes when I come across a problem, I can't use U-substitution on it. So let's look at this example. Let's look at the integral of x squared plus 1 quantity squared dx. Now this one, I'd look at this and say, okay, let's use u to be x squared plus 1. That's been a common theme here. Du is 2x dx. Now, I'm okay with multiplying by 2. I can do that. I can compensate for a missing coefficient like a constant. But I'm not okay with this. I'm missing the x. I can't multiply by an x on the inside and then divide by an x on the outside because I can't have variables on the outside because I can't drag them along like a constant. So this particular problem, and remember before I rewrote this, it was x squared plus 1 quantity squared dx. I can't solve this using U-substitution. However, this is just a good old antiderivative. I could expand this. I'd have x to the 4th plus 2x squared plus 1 dx. And then I could integrate by adding 1 and dividing by the sum of each term. And of course we'd want to find a common denominator and factor out an x. But this is just to show that we can't always use U-substitution. I have to be able to come up with an entire du in order for U-substitution to work. Let's go ahead and look at another function involving a trig integral. Let's look at the integral of x times the cosine of 3x squared dx. Now this time, instead of choosing cosine to be my u, I can't because the derivative of cosine is a negative sign and I don't have a negative sign here. So what I'm going to do is I'm going to let u equal just the argument of that trig function. And again, each problem's a little bit different. Sometimes you'll choose the trig function with its argument, and sometimes you'll just choose the argument. In this case, the derivative of 3x squared is 6x dx, and we've got that one. The only thing I'm missing here, I have the x, the only thing I'm missing is a 6. So I multiply by a 6 on the inside, compensate with a 1/6 on the outside. 6x dx is my du, and then this piece right here becomes cosine of u. So rewriting this, I end up with 1/6 the integral cosine of u du. And again, du is 6x dx. Now remember, this is still the basic idea of Riemann sums. This is the base times the height. I'm summing rectangles here, so that hasn't changed. This process and its meaning has not changed. Now when we integrate, I drag that constant along, I drag the 1/6 along, and the integral of cosine u is sine of u. Now my original problem was in terms of x up here, and so should my solution be, so I need to rewrite this. I need to substitute back in. So this is going to be 1/6 sine of u, but u is 3x squared plus c. Now remember, indefinite integral plus c. Also keep in mind that I need to make sure you substitute back in every time. If my original is in terms of x, your final answer should be in terms of x as well. Okay, let's go ahead and look at another one where we're doing some compensation with a trig function, and we also need to keep in mind our antiderivatives. Now before, in the previous sections when we were doing problems like this, we needed to think, okay, the argument of my trig function could only be x. That's the only way I could deal with these before. But now, because these arguments are the same, 6x, I should be able to work with this in terms of a U-substitution. Now remember, the derivative of secant is secant tangent. Therefore, the integral of secant tangent is secant. So I want u to just be the argument of the function. So u is 6x, du is 6 dx, and I have that, I have the dx, and I can get the 6 in there. So I multiply by a 6 on the inside, compensate with a 1/6 on the outside. So this 6 dx is my du, and then rewriting I have 1/6 integral secant u tangent u du. Now this I can integrate because the arguments are the same and the arguments represent an entire function of x. So these are similar to the problems that we did in terms of antiderivatives. The integral of secant tangent is just secant. So this is 1/6 integral, or sorry, 1/6 secant u. My original was in terms of x, and so should my solution be. U is 6x plus c. Indefinite integral there. So remember, you can check the derivative of all of these to make sure you get your original integrand back to check for your solutions. Let's go ahead and look at another one. Let's look at the integral of sine squared of 4x cosine of 4x dx. Now this one we need to talk about a couple things. This one will be a nice little u du, but the arguments of the trig functions have to be the same in order for this to work. If this was sine squared of 3x and this was cosine of 2x, I would have to rewrite these using some trig identities or use some other technique for integration. The arguments of the trig functions have to be the same. First thing I'm going to do with this one is rewrite it so we see this in terms of a u squared du, hopefully. Now in this particular case, remember on one of our previous ones we said sometimes u is the trig function and its argument, other times it's just the argument. Well, this is a great case of where u is a trig function with its argument. And of course you can't just have a trig function without an argument, you have to have both. Well, if u is sine of 4x, du is the derivative of the sine of 4x, which is the cosine of 4x, times the derivative of 4x, which is 4 dx. And I have the cosine of 4x right here. What I need is the 4. So I need to multiply by a 4 on the inside, compensate with a 1/4 on the outside. And then rewriting, I have 1/4 that I drag along from out front. This piece right here is u, and it's squared. And then 4 cosine dx becomes my du. So this just rewrites to 1/4 integral u squared du. Rewriting, I have u cubed over 3 times 1/4, so it would be u cubed over 12. Now this is not my solution. In order to find my solution, I need to substitute back in terms of x, because right now I'm in terms of u. My original problem was in terms of x, and so should my solution be. So this is the sine of 4x, quantity squared over 12 plus c. That's my solution. Now again, we could check this by taking a derivative. Now one thing I want you to be careful of, I could rewrite this as sine, I guess this is squared. Actually it's cubed up here, I need to fix that. Because of the 3 right here. I could rewrite this as sine cubed of 4x all over 12 plus c. That's an okay solution as well. But I want to avoid this ambiguous notation. Now remember, Maple likes this notation, okay, but to me this is ambiguous. Are we cubing the 4x or are we cubing the sine of 4x? I'm not sure. So let's avoid this notation. But remember, in Maple that's exactly what you'll see. Now, there's another type of U-substitution called change of variable, and these are great problems. They're a lot of fun. And you'll definitely see these. So let's go ahead and look at more U-substitution problems, but they're a little bit different. They're called change of variable. The first one that we'll look at is the integral of x times the square root of 2x minus 1 dx. Now right away this problem has some red flags. I don't have a highest power. If you compare these, this is an x to the first, this is an x to the first. There's no obvious choice here for a highest power. Now up here, if this had been, let's say, squared, then this would have been the highest power and it would have been the obvious choice for u. But I don't have that. So I'd have to work with the problem as is. But we're going to use our gut instinct and we're going to go ahead and start with u to be 2x minus 1. If u is 2x minus 1, du is 2 dx, and we already see problems brewing. What about this guy? Well, let's keep working. I needed 2 dx. So I multiply by a 2 on the inside, compensate with the 1/2 on the outside, and rewrite. So I have the 1/2 out front, integral. Okay, the x is not going anywhere right now. This is 2x minus 1, which is u to the 1/2. And then this 2 dx is my du. So this is my problem, and problem is the right word for it. I'm mixing variables here. I can't mix x's and u's. When you guys get into Calc 3, you'll be looking at double and triple integration. Then you will, but you'll have a double integral sign to deal with it. We cannot deal with this. We cannot have two different variables. So this is why this problem is called a change of variable. I need to take this value right here of x, and I need to change it over in terms of u. And the way I do that is I come right up here and I solve this for x. If I solve this for x, I get x equal u plus 1 over 2. So I bring this u plus 1 over 2 and I plug it in right there for x. So let's go ahead and rewrite this again. 1/2 integral. Now in place of the x, I'll put the u plus 1 over 2. And of course I already have u to the 1/2 du that I'm dragging along. Now this is something that we can integrate this. We could integrate this before when we were talking about antiderivatives before our last exam. The best thing to do is to always pull any constants that you can out front. So this is going to be 1/4 the integral, and then I'll take this u to the 1/2 and I'll distribute it through to the binomial. So this will be u to the first times u to the 1/2 is u to the 3/2 plus u to the 1/2 du. And now I have my good old power rule. Add 1, divide by the sum. I'm going to leave the 1/4 out front, and I want to make sure it distributes, so I'm going to put up a big set of brackets. So I end up with u to the 5/2 divided by 5/2 plus u to the 3/2 divided by 3/2. And I'm going to simplify the heck out of this thing. So 1/4 clear out front, because I'm going to factor this, so there's no reason to distribute that 1/4. I'll have 2/5 u to the 5/2 plus 2/3 u to the 3/2. Well, right now I see that there's a 2 common in each numerator. There's also a u that's common, so I could pull out a 2u to the 3/2, it looks like. And I'll also be finding a common denominator. So again, I said I could pull out a 2u to the 3/2. Let's see what's remaining. I already factored out this 2, so I'm left with the 1/5 u to the implied 1. Okay, I already factored out this 2 over here, so I'm left with 1/3. Finding a common denominator, and I see that I have 1/4 times 2 or 2/4, which reduces to 1/2. So 1/2 u to the 3/2. Common denominator would be 15, so I have 3u plus 5 all over 15. So I could pull out a 15 next. So I have 1/30 u to the 3/2 times 3u plus 5. This is not my answer. In fact, I'm going to be simplifying this even a little bit more once I make my substitution. Now remember, my original problem, if we can scroll up here and find it, my original problem was in terms of x. Right here, x root 2x minus 1. So my original is in terms of x. My solution has to be in terms of x. This is the relevant substitution. U is 2x minus 1. So let's go ahead and substitute in. So I have 1/30. U was 2x minus 1 to the 3/2. And then I have 3 times 2x minus 1 quantity plus 5. Now this is where I get to substitute a little bit more. So I have 1/30, 2x minus 1 to the 3/2. Now here, this is going to simplify to 3 times 2x is 6x. 3 times a negative 1 is a minus 3 plus 5, which is going to be 6x plus 2. And of course, there's a common factor between 6x plus 2, so I could factor a 2 out. And if I factor out a 2, I'm left with 3x plus 1. And 2/30 reduces, and I almost have my solution. 1/15, 2x minus 1 to the 3/2 times 3x plus 1 plus c, constant of integration, because this was an indefinite integral. So this is simplified completely. Now you might say, well, why would we want to simplify this completely? It's a lot of work. Yeah, it is. You get to practice your algebra. Algebra is kind of the most common reason why we do poorly in calculus. Also, we're going to be evaluating these starting in the next problem. And when we evaluate these, this is easier to evaluate in a simplified form than it is to try and come up here and evaluate it if we had just plugged in our x value without simplifying. So let's go ahead and look at that in our next example of definite integrals. Now we already know what definite integrals are, but they're going to work just a little bit differently when we're using trig, or it's not trig sub, U-substitution. Trig sub is something you'll learn in Calc 2. So with definite integrals, we have a little bit of a problem that we have to deal with because I have more than one variable now. I have u and I have x's, and if I wanted to, I could have w's and v's for my substitution variable as well. So first of all, let's go ahead and look at a very easy problem that's a definite integral. So let's go ahead and integrate from 0 to 1, x times the quantity, x squared plus 1 quantity cubed dx. Okay, so I have limits of integration, 0 to 1. Now the thing to remember here with my limits of integration are, what variable are these? So I'm going to start noting that these are x's. How do I know they're x's? Because I have a dx here. So I have three things I can do. One thing I could do is drop the limits of integration. First of all, I'm going to use U-substitution on this, so that's why I'm going through all this. If I wanted to, I could expand this and distribute the x, but that'd be a lot of work. So I am going to use U-substitution on this. So I could drop the limits of integration and convert back to x at the end. I could rewrite using my x equals values and keep my U-sub. Or I could change the limits of integration in terms of my new variable u. So I have three things that I can do here. And I'm going to try and demonstrate each of these in the next few problems. Now, the problem that we're looking at right now, x equals 0 to 1, x times x squared plus 1 quantity cubed dx. Remember, I want to put x equals in here because I need to keep track of what's going on. Now I'm going to let u equal x squared plus 1. We already kind of know this is our technique that we're going to look at. Highest power is x squared. Du then is going to be 2x dx. I have the x, which is grand because I have to have the variable component. I need the 2, so I multiply by 2 on the inside, compensate with the 1/2 on the outside, and I rewrite this. So when I rewrite, I get 1/2 integral. Okay, let's see what we have here. X squared plus 1 to the third. Well, u is x squared plus 1, so that's just u cubed. Now 2x dx, if you look at this one, is my du. So this rewrites to 1/2 u cubed du. Okay, now the only thing I haven't done here is taken care of my limits of integration. So I'm going to kind of combine my first two options here. I'm going to rewrite this using x equals 0 to x equal 1. Now, I could have just simply dropped them, not had any limits of integration until I get clear done with the problem, and I've changed u's in terms of x. But I'm going to rewrite these, and I'm going to keep track of them. But again, I could have just dropped them. Now rewriting here, integration u cubed, u to the 4th over 4 would be u to the 4th over 4 times 2 is 8. Now listen, this is the wrong thing to do. Don't say evaluate from 0 to 1. This is wrong. This is the wrong thing to do. Because if I evaluate from 0 to 1 here, 0 and 1 are in terms of x, and I need to be in terms of u. So what I need to do is to substitute back in to get everything back in terms of x. So again, u is x squared plus 1. So this is going to be x squared plus 1 to the 4th all over 8. That's my solution so far. I have not evaluated this yet. Now I can evaluate this from x equals 0 to x equal 1 because now my problem is back in terms of x's. I think it's easier to pull out all the constants that you can because you're going to get smaller solutions, smaller numbers to work with. So I'm going to pull the 1/8 out front, and let's go ahead and plug in the 1 first. I'd have 1 squared plus 1 quantity to the 4th, that's my upper, minus lower, 0 squared plus 1 quantity to the 4th. Rewriting, 1/8. 1 squared is 1 plus 1 is 2 to the 4th is 16. Now we have to be pretty careful here. A lot of times when we plug 0 in, we get 0 back out. But in this case we don't, so make sure you always plug in and check. 0 squared plus 1 is 1, 1 to the 4th is 4, and I'm subtracting. So I get 15/8 for my solution here. 15/8. Now, when I do this problem, in the third option that I have up here, my third option, change the limits in terms of u, the whole entire problem starts the same. So this is the same problem done a different way, or we could do this. So this problem starts out with x equals 0 to x equal 1, x times x squared plus 1 quantity cubed dx. We let u equal x squared plus 1. Whoops, no fraction bar there. U equal x squared plus 1. Du was 2x dx. Now before I worry about compensation here, right away I'm going to say, okay, let's look at this. Let's change the limits of integration. Let's not drop them or write x equals, let's just change them. Now my limits of integration were x equal 1 and x equals 0. So what I do is I plug 1 in to my substitution. So if I plug 1 in, I get 1 squared plus 1 back out. If I plug 0 in, I get 0 squared plus 1 back out. So, I guess I don't need that. It would be 1 squared plus 1, which is 2. So that's equal to my value of u for my upper limit of integration. If I plug in 0, I get 0 squared plus 1, which is 1, which is my lower value for my limit of integration. So quite a bit to keep track of here. I'm not quite ready to rewrite all of this, but I do know my limits of integration have changed from 1 to 2. And again, they have to be in the same order. The upper limit changed from 1 to 2, the lower limit changed from 0 to 1. So they have to substitute in correctly. Now, going back up here, to integrate this, I need to compensate for that missing 2. So I multiply by a 2 on the inside, compensate with a 1/2 on the outside. This is u cubed. 2x dx is du. So we integrate and we get u to the 4th over 8. Now, I'm done. I don't have to switch back to x because my limits of integration are now in terms of u. So I don't have to switch back to x here. So, pull the 1/8 out front, and plugging in first I get 2 to the 4th minus upper minus lower, 1 to the 4th, 1/8 out front, 2 to the 4th is 16 minus 1 is 15/8. And if you notice, same solution either way, but the important thing to remember here is it doesn't matter which technique you use. It doesn't matter if you change your limits of integration. All that matters is you write things properly. So for instance, up here in this top part, I kept my u's, but I changed my limits of integration from just 0 to 1 to x equals 0 to x equal 1 to show that, you know what, these are not values in terms of u. And then further on along on this one, I changed my limits of integration from x's to u's, and so I showed that change here. Now, it would have been wrong if I had written this as u cubed du, and of course we had the 1/2 out front, and I would have gone 0 to 1. This would have been wrong because these are in terms of x, and they have to be in terms of u. Now if I had written x equal, then I would have been okay. But these are things that you have to be careful of with notation because they have meaning here, and we have to kind of keep track of what that meaning is. Let's go ahead and look at another change of variable problem. Now there's one thing with change of variable that we haven't talked about yet. For this particular problem, let's look at the integral from 0 to 5 of x over square root of 3x plus 1 dx. What ends up happening when we take a function like x over square root 3x plus 1 and we rewrite it in terms of u, we're saying the area underneath the curves are equivalent when I have my limits of integration. So we'll try and write out what that means here in just a second. So experience tells us that choosing our radicand is usually a good start. Doesn't work every time, but it's a pretty good start. If u is 3x plus 1, which is called the radicand, du is 3dx. I have the dx, always will. I can compensate for the missing 3. So I'll multiply by 3 on the inside, compensate with a 1/3 on the outside, and rewrite. So I'm going to have 1/3 integral. We'll figure out what to do with 0 and 5 here in a second. Here I have an x. This 3x plus 1 is u. It's square rooted, so it's to the 1/2. This 3dx is du. So this is my problem right now. So this is a huge clue that I have to use change of variable here, because what's up with this x? I need to change it. I don't want it in terms of x, I want it in terms of u. So let's go ahead and rewrite that. Well, how will we rewrite it? Right here is our key. If u is equal to 3x plus 1, x is equal to u minus 1 over 3. And again, that's just solving algebraically. Subtract the 1 across, divide through by 3. And then I rewrite. And again, I haven't decided what I'm going to do with those limits of integration yet. We'll figure that out in a second. Here I have u minus 1 over 3 all over u to the 1/2 du. So I think on this one, I'm going to go ahead and change my limits of integration. I don't have to. If I wanted to, I could rewrite this and get to my solution and change back to x and evaluate it from 0 to 5. But I usually find that it's kind of easier to change my limits of integration. So let's go ahead and look at changing the limits of integration. So again, x equals 5 is my upper, x equals 0 is my lower. And I plug in 5 into 3x plus 1, and I get 3 times 5 plus 1. I plug 0 into 3x plus 1, and I get 3 times 0 plus 1. So here I get 16, here I get 1, and these are my new values of u. So my limits of integration have changed. Right here they were x equals 0 to x equals 5, and now they're u equal 1, u equals 16. I don't have to change back to x now because my integrand is in terms of u, and so are my limits of integration. So let's rewrite this just a bit. So I have a 1/9 out front. This 3 is not in the numerator, it's in the denominator. So I have a 1/9 integral u minus 1 all over u to the 1/2 du. And again, my limits of integration are u equal 1 to u equals 16. Now, this is the note that I wanted to make here real quick. What this problem is saying is the integral from 0 to 5 of x over the square root of 3x plus 1 dx is identically equal to the integral from 1 to 16, because remember these are in terms of u now, 1/9 integral u minus 1 over u to the 1/2, which is square root of u, du. These are identical. Now the graphs are not the same. The graphs are going to look different, but the area underneath the graphs from the left hand one from 0 to 5 and the right hand one from 1 to 16 are identical. And that's not a u, that's a u, not a 6. So I could integrate either one of these, and what we're working toward is integrating this one. So let's go ahead and start working on that integrand. So I have a 1/9 out front, integral from 1 to 16. Now the easiest way to work with this is to think about this as flipping this up top. If I flip that up top, it would be u minus 1 quantity, remember it has to distribute, u to the negative 1/2. Or I could think of this as u over u to the 1/2 minus 1 over u to the 1/2. Either way, when I rewrite that, I get u to the positive 1/2 minus u to the negative 1/2 du. So it doesn't matter which way you just choose to rewrite it. Algebraically, these are the same. Dragging the 1/9 along, and I'm going to integrate, and as soon as you integrate, you drop the limits of integration. Or sorry, you drop the integral sign and the limits of integration. So when we integrate, we get u to the 1/2 plus 1 is u to the 3/2 divided by 3/2. U to the negative 1/2. If I add 1 to a negative 1/2, I get a positive 1/2 divided by positive 1/2. And then I can rewrite, and again that 1/9 is out front, it has to distribute through to both terms. I get 2/3 u to the 3/2 minus 2u to the 1/2. And again, I'm going to simplify the heck out of this. I can definitely pull out a 2. I already have the 9 out front, and I can pull out a u to the 1/2. So if we pull out a 2u to the 1/2, I'm left with 1/3 u for my first term. Okay, and again, minus 1. Minus 1 because I pulled out a 2u to the 1/2. Finding a common denominator, I have 2/9 u to the 1/2. Common denominator here would be 3, so I'm going to have u minus 3 all over 3. And I have a 2/27 square root of u minus 3 evaluated. Now remember, I have my limits of integration in terms of u now from u equal 1 to u equals 16. I don't have to convert my solution to terms of x. I can leave it in terms of u because I've switched my limits of integration to values of u. So 2/27 I'm going to pull clear out front, and again the reason I simplify this is, first of all, it's fun and it's good algebra practice. Also, it keeps my number smaller. So I have 2 27ths, clear out front, and then I plug in my upper minus my lower. Plugging in my upper, I'll have square root of 16 times 16 minus 3, there's my upper, minus my lower, square root of 1, times 1 minus 3. 2 27ths out front, square root of 16 is 4, 16 minus 3 is 13, 1 minus 3 is a negative 2, minus a negative 2 is the same as a positive 2. So I have 2 27ths, 13 times 4, that's like a deck of cards. 13 times 4 is 52, plus 2 is 54. And of course 27 times 2 is 54, so I get 4 here for my solution. That's some sort of area. I don't know if it's true area or signed area, but that's my solution. Now if I wanted to, I could have gone back and not changed my limits of integration, kept them in terms of x, gotten my solution in terms of u, and once my solution was in terms of u, switch to x, and then evaluate in terms of x. And it doesn't matter to me which way you do this. It's irrelevant which way we have this happening, as long as you show your work and use the proper notation. And proper notation is very important here. Let's do one last problem. Let's do a trig function. So let's look at the integral of cosine of 2x over 3 dx evaluated from 0 to pi over 2. Just a quick side note. Sometimes people have problems with 2x over 3. We're going to have to take its derivative pretty soon, so let's talk about it now. 2x over 3 is the same as 2/3 x. Okay, they mean the same thing. Now the derivative of 3x is 3, so the derivative of 2/3 x is 2/3. A lot of people look at this, and when they try and take the derivative, they use a quotient rule. But remember, it's easier just to recognize that these are equal, and when you take your quotient rule, you'll still get 2/3 as your derivative. So just realize that those are equivalent statements and treat them as such when you're working your problem. Okay, well, we can't let u equal cosine 2x over 3, because if u is cosine 2x over 3, I would need a negative sine 2x over 3 times 2/3. I can get the 2/3 in the negative, I can't get the sine. So I'm going to let u just equal the argument of my trig function, which is 2x over 3. If u is 2x over 3, du is 2/3 dx. I need to compensate for that 2/3, so I multiply by a 2/3 on the inside, compensate with the 3/2 on the outside. So rewriting this, I have 3/2 integral cosine of u du. Now what about these limits of integration? Well, let's go ahead and change these. So if we change our limits of integration, I have x equal pi over 2, and my lower limit of integration was x equals 0. And I need to plug this into 2/3 times x. So I have 2/3 times my value of x, 2/3 times my value of x. Well, my lower limit of integration doesn't change, u equals 0. Now my upper limit of integration, the 2's cancel, and I'm left with pi over 3. And these are values of u. And I'm going to note that they're values of u just to keep things pretty clear here. Now I need to drag along this 3/2. The integral of the cosine of u is equal to the sine of u, antiderivative. The derivative of sine is cosine, therefore the integral of cosine is sine. The 3/2 is just drug along here. Now, do I need to change this u to 2x over 3? And the answer for this case is no, we don't. We don't need to change it because I've changed my limits of integration. If I had not changed my limits of integration, I would have had to rewrite this as sine 2x over 3 and evaluate it from 0 to pi over 2. But because I changed my limits of integration, I now evaluate this from u equals 0 to u equal pi over 3. Pull that 2/3 out front, keep your numbers smaller, less cluttered solution, and I have the sine of pi over 3 minus the sine of 0. And of course we see right away that the sine of 0 is 0, and so rewriting here, I have, oh sorry, that's not 2/3, that's 3/2. It's 3/2 from right here. I just copied it down wrong. So we have 3/2 times the sine of pi over 3. The sine of pi over 3 is square root of 3 over 2. So this is 3 root 3 over 4 is our solution. So this is some sort of area. I don't know if it's signed area or if it's true area, but it's some sort of area that we're representing here. So things to remember here: show all your steps, show your U-substitution, show your changes in your limits of integration if you choose to change them. If you don't change them, make sure you're writing x equal or you're writing u equal to distinguish between which variable you're referring to in terms of those limits of integration. Knowing how to integrate effectively, knowing how to recognize when to use U-substitution and how to use U-substitution is one of the most important skills you can take out of this class. So we're going to practice these, and if you have any questions, please let me know. Thank you.